This is Andrew Torres's circuit board. As you can see, there is a mess of wires here. A lot of loose wires, a lot of, weaving and stuff, but it is color coded to an extent. The green wires are almost like everything to do with input A. So like here, there are 4 green wires that correspond to the switches 1 through 4, which is input A. These green wires run through the multiplexer 1. This is also multiplexer 3 in our diagram. And then this is the flip-flop 1. So there are a lot of green wires running between these 3 chips. And then also this is the adder, so there are green wires there too, because this is all coming from the A input. The B input, which corresponds to flip switches 5 through 8. These are the yellow wires. So the yellow wires start out with multiplexer 2 on the diagram. These go to multiplexer 3. And then, let's see. Well, sorry, these go to flip-flop 2, which then goes to multiplexer 3, these yellow wires here. And then because I ran out of yellow wires, I also used blue. So blue also has to do with the B input. And then these blue wires come from multiplexer 4 and connect to the flip-flop, and then they display the B input here. The white wires, which are coming from this flip-flop 1, these are like the not the input, but the output, sorry. Like the X output. Blue wires are the Y output. So in the end, like when we run our test, we should get the white wires displaying our greatest common divisor. Yeah, so just a quick run through. Oh yeah, and this is the clock too. So this is the button that runs the clock. And then this button here resets the test because it connects to the clear pins of the flip-flops. So yeah, 2 flip-flops, 4 multiplexers in adder, and then the clock over here with the Schmidt inverter. So let's run our tests. Our first test, and I'll actually reset just in case. So I reset. Our first test is A equals 4 and B equals 7. So I'll flip the 9 switch, which is our S1. So now I'll input A equals 4 and B equals 7. And then we'll press the button once. So as you can see, we have these lights on here. Now we flip the signal off so we can do new numbers. And then we'll keep pressing the clock until only an X output is showing, because that would be our greatest common divisor. So it's doing the Euclid's method. And then I'm pressing the button, but it's not changing, so we know that's our greatest common divisor, which is 1. That's the correct answer we were looking for. The greatest common divisor of 4 and 7 is 1. Okay, I'll turn all of these switches off, and I will press the reset button. Okay, so now we'll do our second test. We have we'll flip on the 9 switch, the S1 switch. We have A equals 9. And B equals 6. Okay, press the button once, the clock, switch off the subtracting switch, and then keep pressing the button. And this will be our greatest common divisor of 3, which is also correct. That's what we were looking for. Okay, last test. We will do 2 equal numbers. I thought that would be kind of interesting because it should be the number itself. So let's do 5 and 5. So we'll do 4. Shoot. Oh, sorry. Gonna reset. We'll flip on the 9 switch first. Then we'll do 5. Nope. Let me get this here. Yeah, so we have 5 and 5. Yeah, there they are. And then we'll keep pressing. Oh, shoot. We'll switch off that 9 switch, and then we'll start doing it. There, and I'm pressing, and of course, like, it didn't really require any a lot of subtraction, because the greatest common divisor of the two inputs is the number of the input itself, which is 5. So yeah, all our 3 tests worked.